Uh, okay, so today we're very happy to welcome Lek-Heng Lim from UChicago, who will speak about mathematical snippets from AI.
Thank you very much. Well, thank you. Thank in particular to Akil for inviting me. It's a pleasure to be here in the math department. Talk about some of my work. Okay, good. So now, so as the title suggests, it's going to be a little bit about AI. Right, it's going to be very much influenced by my own interests. Okay, and there's going to be significant amount of math, at least in my perspective. There's going to be quite a bit of math. Okay, now so there's going to be some algebraic geometry, but it's lowbrow algebraic geometry, the kind of algebraic geometry that I would understand. Okay, but hopefully it'll be of interest to you. See how the work that you develop, right, highbrow algebraic geometry ultimately can be filtered to applications. So the goal is not so much to prove deep theorems, okay? Ultimately, I'm computational and applied mathematics, and I want my work to be relevant to practitioners, to engineers, and AI. Of course, at this point in time, AI is primarily an engineering topic. Okay, it's done with a lot of things that you would find unsatisfactory. Okay. Now, so my goal would therefore be utilitarian. Okay, and there are three goals that I have for this talk in particular. One is to improve, right, something that engineers are doing. Right, can I accelerate this algorithm called SGD? It's a very simple algorithm, but it's the workhorse of AI. Essentially, it drives like the AI revolution. It's also driving up the price of NVIDIA chips, okay? And it's essentially used to run SGD. Now, I would clarify, right? Try to clarify. It's the three goals. Essentially, right, trying to improve, trying to clarify. And I would clarify one particular conjecture. It's not so common to find conjectures in computational applied math or engineering math, but in this case, there is one famous conjecture, and that I made some contributions to. I'm going to tell you about that. The last point, unfortunately, I would not have time to talk about that. We have more slides than I could covered in our long talk. But if there's going to be sort of insights that I surmise from pursuing this. There's this very important model, the transformer. Happy to talk more about it offline if you are really interested. And it's a mysterious object. Okay, so in fact, it's a reason why AI is feared, right? Because people don't really understand how it works. And I believe I have some insights from mathematics to share about this. But unfortunately, I won't have time to talk about that. But I'll talk about snippets. Okay, and one of it that came from my investigation of transformers. Okay, and very basic difference between what you typically do in math, in particular in economic analysis, and in AI, okay, or machine learning, right, in both synonymous, is in how you would treat a complicated function, right? So, in harmonic analysis, or more perhaps I could say computational harmonic analysis or approximation theory. What you do if given a complicated function is that you're going to decompose it as a linear combination of simpler functions. Okay? Now in AI, that's what they used to do too. Okay, so a lot of AI used to be like just approximation theory. Okay? But recently, people realized that it's actually a better idea to not use sums or linear combination, but to use composition. Okay, well, and of course the thing is we go outside analysis, right? If you pick any book in algebra and math book in some area that's not analysis, let's say algebra, geometry, topology, you would see diagrams like this. Okay, so it's hardly new in mathematics, right? Every book that you pick up in math would essentially show diagrams that's like this, or even like 10 times more complicated than this. Okay, so basically decomposing maps as composition is not new. Okay. Now, of course, there are a lot of upsides. One of the reasons is that one of the upsides, as you can see immediately, is that you get to choose the spaces in the middle. Okay, whereas if you decompose as a sum, you don't get to choose all these domains and codomains that appear in the middle, and this is important. Okay, and I will give another important reason, right? More like a comparison. When I try to decompose a complicated function as a sum, okay, or linear combination, basically you face what's called the curse of dimensionality in applied math. Okay. Also, the only way we know how to well, let's assume high dimension. Okay, we are talking about function on a high dimensional space. This n here is, well, number of pixels in an hour-long movie in every frame, so it's a huge number. Okay. Now, so the thing is, the only way we know, right? At least I know, to decompose, to construct a basis function in high dimension is by taking tensor product of basis function in low dimensions. If you do this strategy, right, you construct your basis function out of low dimensional basis function, tensor product of low dimensional basis function, you're going to get a huge explosion in the number of parameters. The parameters is going to scale like n times d to the n. Okay, d is the number of summons, right? Let's say it's all the same in every dimension. Well, the smallest d you can take is 2. Okay, I mean, if it's 1, it's already, you can't write as a sum. Okay, so it's 2. Okay, if it's 2, this is already exponential. Okay, now the thing about composition, okay, is that, as I said, you get to choose the spaces in the middle. Okay, even if you choose all the spaces in the middle, right, choose all of them to be Rn, you can actually build some pretty sophisticated function. My example is a neural network. Okay, so you take the maps to be all linear. Okay, you take the maps to alternate between what's a very simple nonlinear map, signal I, that's parameterized by a single vector, and matrices. Okay, so it's very, very simple. Okay, and the parameters, the number of parameters involved is much smaller. Okay, it's only polynomial at n. Okay, okay, and upside is that, well, given modulo various conditions, d can be chosen to be small, right? Here's results on this, and you can even impose structures on your AI. Okay, on this linear maps. For instance, the linear maps can be couplets, Hanko. Okay, so the linear maps don't even require n squared number of parameters. You can specify them just order n number of parameters. So that is a huge reduction of number of parameters involved required to write down that map when you go from sum to composition. And I think that's the key. Okay. Now, there are other upsides. Okay, one is that you don't lose like various nice features that comes with sums. Okay, well, invariably, at some point you're going to have to differentiate your function. Okay, if you differentiate a sum, well, of course, the derivative behaves nicely, but it also behaves nicely, equally nicely, when you do composition, right? When you differentiate a composition of functions, well, it becomes a composition. The derivative is precisely the composition of the linear maps that are the derivatives. Okay, so that's a very nice feature. Well, in fact, that underlies this algorithm called backpropagation in machine learning. Okay, backpropagation is simply the statement that if one of that space, right, the last space is real numbers, right, one dimension, right, and that's always the case because you always have to use the loss function. Then, if I want to compute the gradient of this composition of this chain of function, right, it's always easiest to multiply from the back to the front. Why? Very simple, because it's like you take matrix, multiply by vector, you get a vector, and the next step you take a matrix and multiply by vector. Now, if you do it in any other way, right, let's say you do it from the front to the back, then it's going to involve multiplication of matrices, and that is very, very expensive compared to multiplication of matrix with vector. Okay. Other thing is there are other nice features, like for instance, G equivalent. You want to construct a G equivalent map, right? It's sum works well, right? Sum of G equivalent maps are G equivalent. You're going to do it with composition as long as I choose every piece to be G equivariant. You get every component to be G equivariant, you get G equivariant. Okay, now, so the thing is, talking to some of the students here while waiting for the talk to begin, notice that most of you are like highbrow mathematics, okay? So you may not be familiar with some lowbrow stuff like in engineering, like for example, machine learning, okay? One of the greatest machine learning theorists, I step into the room. Thank you for coming, Natty. Right, so machine learning in one sentence, right? Let me know if you disagree. Okay, now basically this is machine learning. It's very simple. Okay, what is it? It's a function. Okay, that you do not know. Okay, takes domain A to elements in codomain B. Now, given A and B, find a function F. Okay. Now you're given, of course, not all of A and every possible A. You're given some A. Okay. Now you want to find F. Obviously, when you put it in this way, it's very, very close, right? And numerous, uncountably many, but assume A and B are big sets, uncountably many F you can pick. So it's very ill-posed. And the thing is, it's undoable because there are uncountably many, well, F, right? Uncountable in a bad way, in fact. Okay, so you need to restrict the choices of F. Okay, so the thing is that's called a model. Okay, I need to assume that my F takes a certain form, and ideally, it's going to take the form where it's parameterized by some set that is finite dimensional. Okay, let's say some manifold that sits in RP, embedded in RP. Okay, so P is the number of parameters. Okay, and X here denotes the number of parameters. Okay, and I'm going to make further assumptions. None of it very stringent, like all this input and output domain and codomain are subsets of Euclidean spaces. Normally, there's a way to do that. Okay, like even if you have languages, like you would just encode them as vectors in some high-dimensional space. That's sort of a basic feature of a transformer. Okay, so this is the premise. So let me give you a little bit more details. As I said, you're not given every point A and B. You're given a sample, right? A sample of dimension M. Okay, that's the word that people use in statistics of sizing. Okay, M is a finite number, but it's going to be a huge number. Okay, it's going to be sort of a number that could only be processed by computer. Okay, I guess that's where the machine learning decides to differ from statistics. Okay, now the thing is, I want, of course, my model to take AI, but to the others. Okay, now I don't want it to be exactly equal. Okay, that's for overfitting. That's that. So I want it to be approximately equal, right? Approximately phi, right? When I call my parameter x, phi, with parameter x should take AI to be up. Okay, and what do I mean by approximately equal? Is going to be measured by some loss function. The simplest loss function, right, will be the norm of the difference, or the norm of the difference squared. But for problems like classification, the loss function can be more unexpected, right? Hinge loss and things like this. Basically, this is machine learning. Okay, and I'm going to find my parameters. So I've given all this data. I've given my model. I chose my model. I chose my loss function. Now I'm going to find my parameter. This is the basic problem. This is for empirical risk estimation. Okay, I'm going to find my parameter x. Okay. Okay, so for linear regression, it's very simple. The class of function I'm looking at are the linear functional. Okay. So linear functional risk representation tells you that it's always going to be given by the inner product. So your model is exactly given by the inner product of A, right, the data, with the vector of parameters. Okay. Well, for neural networks, it can be more complicated, right? And a lot more parameters, right? That's the neural network that I showed you earlier. But basically, you can think of it as a set of dimension dn squared plus d minus 1n. Okay, that's the number of parameters that's involved in a neural network. X is a huge dimension vector. Okay, but it's already much, much better than doing the sum model, okay, where you have to deal with exponential number of parameters. Okay, okay, well, it's transformers, right? What I would not have time to talk about. This phi, right, with that parameter x is going to be given by this chunk here, okay, on the left side. Okay, the thing is, what exactly is this? Well, this is sort of the way it's presented in engineering literature, where functions are not stated in terms of maps, they are stated in terms of flowchart. Okay, so you have to decipher this. And I think I did. Okay, right. So that's the last part. I won't have time to talk about exactly what this object is. Okay, what this object. Okay, and this, of course, is something that's very, very mysterious, right, and very, very important. Right? Now, but let's save that for maybe a future occasion. So the bottom line, right, and summarize is very simple. Given data, given model, given a loss function, I want to minimize this function. Okay. Now this function is going to be what every data point, AIBI, I want my parameter to have a good fit. Okay, so I want to minimize this piece. And since there are m data points, right, I am going to have to optimize a function that has m summons. Okay, but it's very, very rudimentary, very, very fundamental problem in modern AI. So ultimately, the function is going to take a form like this. So it's going to be a sum of m functions, right? I put a 1 over m for a very good reason. You'll see why later if you do not already know. So there's a big problem, right? One big problem is that this is x is high dimension, right? Even for a neural network, as you can see, the p is huge, okay? Well, it's massive too, okay? In modern problems, in order to fit a model with so many parameters, you need a lot of data, okay? That's big data. Big data means massive, okay? M is large, okay? So that's huge number of M. This number of summons in this sum is enormous, okay? Okay, so as you can see, right, even though each of this piece, right, is going to come from a composition, ultimately I still need to work with a sum, okay? Now, so the thing is, how would I optimize a function like this? And notice that Nappy gave a talk a couple weeks ago. So presumably you already know the answer. The answer is due to a pair of say statistician, but maybe also mathematicians, Robinson Monroe, 70 years ago. Okay, Robbins is I guess what's his I don't remember his first name. Herb Robbins. Okay, that's the guy who wrote What is Mathematics with Richard Huron. Okay, well, one of the very first math book I ever read. Okay, now so to some extent he's a mathematician, right? Monroe, I guess, is not mathematical in any way. It's was a dean of Harvard College, right? You know, more like I think more like a social science person. But anyway, they wrote this famous paper, right? You know, it's one of the very few papers that's still in actively cited today, right? And they define this algorithm, right? Maybe some people call it Robinson-Monroe, some people call it stochastic gradient descent when it's applied specifically to this problem. So it's very simple, right? You know, if I want to do optimize that function, the most basic thing I could do is to compute its gradient. And we have a great way to do that, right? Remember, we have back propagation, which is chain. Okay, so there's a great way to compute that gradient, right? In fact, there's a great way to compute all this gradient. Okay. Now the thing is, the trouble is there are too many pieces here. Okay, in order to compute the gradient of f, I have to compute all this. No. Well, so it's you know, if I have to compute all this gradient before I make an update, it's going to take forever, right? So what we're going to do is we are going to just compute one, okay, which is already very, very expensive. Okay, that's why NVIDIA stock prices have to go up, right? Because the only way to compute that is with servers of GPUs produced by NVIDIA. Okay, to compute this, just this thing, okay? Now, so how do you choose which one to choose? You choose it randomly, okay? The beauty, right? If you do not know how to do it randomly, okay? Now, you just do it randomly in a way, let's say uniformly randomly. So the index 1 to m, you choose that I randomly. So at case step, you choose something that's random. And well, I think it's straightforward exercise and probability to show that the expectation, right, is going to be the whole gradient. Okay, so even though it's not good, it's not great, right? You know, it's going to converge in expectation. That's what Robbins and Monroe show. Provided you choose your eta k appropriately. Okay, eta k is called the learning rate. Okay, now you can also slightly generalize, like instead you have more NVIDIA GPUs than most people, then you can actually afford to compute more than just one of this gradient. You can compute, let's say 5. So I'm just going to sample a subset of 5 from 1 to m, right? This is SK. Okay, and then do it in what's called mini batch fashion. Okay, this size of this SK is called mini batch. Now, of course, there are a few questions, right? I'm going to first talk about later on. I'm going to talk about this. Whenever you choose states randomly, whenever you sample, there's always this question: should I sample with replacement or without replacement? Okay, that's a big question in machine learning. It seems like a nothing burger, right? It's actually important. Okay, I'll say why later. So before I get there, right, that's going to be sort of the meat of my talk. Let me talk about a piece of work that was recently accepted, and I'm sort of quite excited about. Now, so as I said earlier, right, you cannot choose your learning rate, that coefficient in your stochastic gradient descent in SGD randomly. You need to choose it so that it goes to zero fast enough, but not too fast. Okay. Now, what does that mean? So in Robbins and Monroe's original algorithm, they had this beautiful condition. It's one of the best known condition involving series, right? Well, the sum of the coefficient must be infinity. Okay, it must not go to zero too fast, but the sum squared must be less than infinity. Okay, it must be finite, it must be convergent series. Okay, in particular, they must all go to zero. Of course, this is very simple, right? And was in the first paper. There are many generalization. Okay, one of it recommended one by Goreski, right? In fact, you can choose that independently. Okay. Now, problem is that these are convergence results. Okay, in the sense of what you do in math, right? It's a math result, limit n goes to infinity, something must happen. Well, in reality, in the engineering reality, nobody has time to wait for n to go to infinity. You want it to be as fast as possible, right? So you cannot do n goes to infinity. I want to know how fast. If I do 5 steps, right? I go over my data 5 times, right? Is that enough? It's called 5 epochs, right? You need to answer questions like this, okay? Now, so the thing is, obviously, I'm going to try to choose my eta k, my learning rate, in a way that depends on my function, right? This means that I don't have to choose it. Now, you don't see anything, right? This condition doesn't involve the function, right? I can choose eta k to be 1 over k. It's going to satisfy this, right? Right? So that's a perfectly good eta k. It doesn't depend on the function. Surely I can do better than that. I can pick it in some way where it depends on the function. Okay, so the thing is, now, these are essentially like the currently popular approach by Basila Gowai, right? It's actually old, something that's fairly old, is to choose it based on this formula. Okay, now you can see that the gradient appears. Okay, I should have put IK. Okay, this is not the whole gradient. Okay, and this, well, has one problem. It involves 2, right? At least to me, right? It has one problem. You can see it. It's very easy to speed up the numerical algorithms by using more past iterates. Okay, this uses 1 more. It requires you to know what you did before. It's not, it depends on k minus 1, what you did at the last step. But ideally, I want something that doesn't depend on that. Now, there's another one, right, due to Norcidel at Northwestern, or up north. Well, that's even worse. Okay, it requires you to have a history. You need like 5 previous iterates in order to construct your eta k, right, which you replace by a matrix, right? This matrix is intended to be like the inverse of Hessian. Oh, by the way, I should say why you don't use Hessian, why you don't use Newton method. Well, the reason is because it's simply unaffordable, but even storing a vector is outrageously expensive in this setup, okay? Now, there are other methods, right, involving momentum, right, initially due to Nesterov, but with a huge history, right, including Natty has done fantastic work on this, on moments, okay? And the most famous paper in this, right, this paper has 180,000 citations. I looked it up yesterday by 2 guys, right? There's one from Google, the other one from Harvard right now, right? And essentially, what's the problem with this? They work very well, okay? Problem is that it requires a lot of what's called hyperparameters, okay? I mean, meaning that there are a lot of unknown parameters that you sort of have to find out through engineering solutions, like trying to solve a small problem, like, even applying machine learning to learn what those hyperparameters ought to be. Okay, now the thing is, my algorithm, right, of course, I think it's superior. Okay, it's going to require no hyperparameters. Maybe 1, okay? Maybe 1 if you use the batch size, if you use the batch state, the mean batch state, then you need 1, okay? So basically that's it, okay? And everything is sort of a single step. It only depends on the current iterate. Okay, there is no k minus 1 in here, okay? So, and this is motivated actually by univariate optimization. It's, I'll say a few words about that. And compared to other algorithms that don't require a huge number of parameters, okay, mine behaves very well with respect to condition number. Okay, positive or 1, condition number. Well, by the way, it's for convex function. Convex function has a condition number. If you don't know what it is, just think of it as the condition number of the Hessian. Okay. Now, BRGS, it depends on the history, right? So it's the worst. So basically, well, ours don't. Okay, it's only condition number squared. But now the thing is, proof, right, in the pudding is in the ink. So you have to run it on real data, and we did. The black line is our algorithm, so this tells you the number of passes through the data. This tells you about the running time, right? Usually in a sort of more applied talk, I would have a series of diagrams like this, and I'll spend out well on this and to convince you that it's really good. But since this is a math audience, I'm just going to show one. Okay, so one is typical, right, of other examples. Now the thing is,
For this math audience, can you tell us what it is?
this is yes. Okay, so basically, I told you about a couple of different algorithms, right? I told you about plain vanilla SG. Let's say I just pick my learning rate according to what Robbins and Monroe did. I told you about SVRG, is an improvement of that, where you use something called control variant. Okay, every couple of steps you evaluate the whole gradient. Okay, done by one of my academic siblings, right? Very popular. SVRG BB is well boundary level 1, right? But with this control variant put in, yes. So the y-axis, okay, this is essentially telling you how close it is to the optimum. It's the fxk minus fx star properly scaled. Okay, and this tells you how many passes you need to run to the data, right? This tells you the run time in seconds.
There should be -1, -3, -5, not 10 to the right log.
Possible. Yes, you might be right. Yes, thank you. So, but basically, well, you know what I'm trying to show you is that my line, the black line, is the lowest. Okay, the lowest is always the best. Okay, lowest means it's the fastest. Okay, right. Okay, good. So, again, I'm happy to discuss this offline if you are really interested in this picture. So let me tell you the inspiration. How did I find this? Okay, now basically, if you look at univariate, okay, it's always good to, well, I guess it's one thing that engineers and pure mathematicians have in common, right? Sort of the mathematical philosophy, right? You cannot do a problem, right, with many variables, right? There's a smaller problem they cannot do, right? So I can find that. And the smallest problem they cannot do usually would be univariate. So you will try to look at that one, okay? So if you try to do an iteration of this one, so I guess steepest descent, use a method would all be of this one. The various ways to treat the denominator, okay? Obviously, you're going to need your derivative, okay? Now, the thing is, if you choose the denominator to be Newton, okay? Right, that means second derivative. Well, then it's quadratically convergent. That's the fastest. Of course, Newton method is out of reach, right? As I said, it's going to involve n by n evaluation of n squared function. That's definitely not possible for modern AI applications. So is there a way for you to avoid second derivative, no f double prime, and still get quadratic convergence? So, well, intuitively, the answer should be no, right? If there is, why do we not know about it? In fact, the answer is yes, okay? Something called Stephanson's method, we use this. Okay, this is called the divided difference, okay? And it is, in fact, going to give you, right, it's actually a fairly simple exercise, just Taylor series, do a Taylor expansion, right? And then you actually see that it's as good as Newton. Well, what's the problem? The problem is that it doesn't generalize to multivariate. Newton generalizes easily when you have not, right, xk and r, but xk and rn. Okay, Stephanson doesn't. At least nobody knows how to do it in a cheap way. Okay, only way to do it is to make it as expensive as Newton. So I guess to some extent we figured that out. Okay, we figured out how to make this. We actually learned the trick from the quasi-Newton people to extend this to multivariate forms. And the thing is, frankly speaking, as a numerical analyst, this is a bad thing. Okay, this is a bad thing for the computer because you might dividing by a quantity that could go to 0. This is unstable. Well, and if you try to do it without that stochastic component, you don't do it randomly, it's better. Okay, but if you do it randomly for some reason, it works. Okay, like this. Okay. Okay, so
This is just the choice of xk.
it's just the choice of eta. This is just how. In fact, there's even a way for me to improve this order of convergence to 1 plus square root of 2. Okay, what people call the silver ratio, but this is the golden ratio, as you might recognize. So the Taylor ratio, right, is something that is, so it's bigger than 2. It actually is super quadratically convergent, provided I introduce another parameter, and that parameter I'm going to use the Barzilai-Born step size. Okay, and it's my conjecture is that it's impossible to do better than this. But the problem with introducing the Barzilai-Born step size is that it becomes multi-steps, and I want it to be single step. Okay, it has to be only depend on what start date computed this xk. Okay, now the thing is, this is sort of the improvement part. Well, I'm not sure it's going to fly, right? Ultimately, it works if people are going to use it. Yes.
Yes, I can clarify what this convergence the polynomial rate, or is this a constant somewhere? Or
Oh, yes. So this is the definition of the order of convergence. Okay, but so of course in real analysis, right, that you teach in the department, you only care about whether a sequence converge, right? So here we care about how fast the sequence is going to converge.
That's Q.
Yes, Q. Q is this Q here is the I sort of so Q is
Yes,
golden ratio if I use secant, right? Q is 2 if I use Newton, and Q is 1 plus square root 2, right? Currently it's called a silver ratio. I learned it from my students. Okay, we use Stephenson combined with the Barzilai-Born. Okay, yeah. So now the other question, right? So as I said, I'm going to do 3 things, right? Actually 2. First thing is that I'm going to improve existing algorithm. The second thing is I'm going to clarify. Okay. Now there is, like I said, one of the fundamental question when you sample is that you have to ask, is it with replacement or without replacement? It seems like a minor distinction, right? Maybe not to a probabilist, right? And to engineers, it seems minor. And in fact, if you look at your papers, right? Maybe even Natty's paper, you see this. Okay, when they prove a theorem, they assume that it's with replacement. Okay, every time you sample is from the same set. Every step is independent of the next. Okay, well then why? Because it's much easier to analyze, right? When you sample with replacement, every step is sort of independent, right? When you sample without replacement, you have to think about what happened in the previous step. Okay, so theoretically, and almost all theorems that you see in the literature will be proved, assuming that you're doing it with replacement. But if you look at how the algorithms are actually implemented, they're implemented without replacement. Why? Well, again, intuitively, it's sort of clear, right? I've already looked at this point. Why should I look at it again? Right? It's something that I already computed in one of the previous steps, right? Why would I look at this again? It's old information, right? And it's also much easier to implement, right? I don't have to put it back, right? It's so almost all implementation, maybe I'm wrong, I haven't looked at many, okay, and the ones I look at are done with replacement. Essentially, there's just a random reshuffling. In fact, it's also used, that term is also used for sampling without replacement in the context of SGD. You just randomly reshuffle 1 to n. It seems like it wouldn't make a difference, but it does. Okay, in reality, random reshuffling makes a difference, and we'll see that in a minute. Right? It's there are theoretical evidence, there are empirical evidence that without replacement is better than replacement. Okay, and we'll see some actual examples. Let's try to analyze this. Obviously, f can be any function, right? It depends on the model that you have. So how do we analyze a problem that depends on f that can be arbitrary? Well, you don't, right? So what you do is you typically look at some examples, some specific cases, right? And one of the most common cases, right, that everybody has to look at, right, when you analyze an optimization algorithm is when the objective is a quadratic function. Okay. Why? Because one reason is that, that's how we normally do optimization. We don't deal with every function. We're going to look at approximate every function as a quadratic function as its second order Taylor extension. So this is relevant for more than one reason. A quadratic function. And you can of course write it in the form where you can apply SGD. Now, another case, but because we are talking about SGD, is when you look at a sum of quadratics. Okay. Now the thing is, my algorithm, right, stochastic Stephenson method, when you apply it to f, the first case, it gives you a well-known algorithm. So there's another reason to favor SSM. Okay, SGD doesn't. Okay, I give you this algorithm called Katzmark's algorithm. Again, a very old algorithm. So what it does essentially is compute this term. Okay, minimizing a quadratic and solving a system equation is more or less equivalent. So we might sort of assume that we want to solve the x equals b, this system of the equation, and we're going to compute this. Okay, that's ignore the case where you know the denominator can be small. Let's assume that it goes through. Okay. Now this algorithm was invented by Max Marx. Okay, it's not very well known until about 20 years, well, you know, more like 15 years ago, right, when it was randomized. Okay? And people believe that this is because, you know, it's actually like you know, a special case of SGE. Actually, it's not. Okay, SGE actually doesn't give you this, but my method SSM actually specializes in this particular case. Now, when you randomize, basically this is what you have to compute in the iterates. Okay. Now, and what they observed, right, Thomas Stromer and Roman Verschainen, discovered was that if you do this randomization compared to the original one, it actually dramatically improves your convergence rate. For some reason, this is empirical. Okay. Now, so random reshuffling is good even if you don't have to do it. Okay. Okay. So now, so the thing is, let me get to my problem. Ultimately, I'm going to present a conjecture, okay, that I'm going to resolve with some lowbrow algebraic geometry. Okay, and I'm going to tell you how that conjecture is, we arrive at a conjecture. I'll really try to analyze this algorithm, right? You can think of it as an algorithm for solving a system of linear equation, or you can think of SGD applied to a quadratic function. Then the thing is, you want to see how fast the error goes to zero, right? Error is xk minus x is execution. Now you realize that, well, this algorithm has a very nice feature. Okay, the error at step k plus 1 is a projection of the error at step k. Okay. Now, what do you know about this orthogonal projector? Okay. What do you know about orthogonal projectors? They are actually symmetric positive semi-definite matrix. Okay, or symmetric more negative positive definite matrix. Okay, so this is something to keep in mind. So basically, if I do this, right, at every step, ultimately I'm going to end up with a product of projector, so that's going to be a product of positive semi-definite matrix. And the thing is, I need to compute the expected error. Of course, the expected error is going to depend on whether you do it with or without replacement. To do a simple case, let's do n equals 2, right, to k equals 2 steps, right, the sum has 2 terms and 2 steps. Now, if you do it with replacement, right, then you need to, right, it's possible that you look at the same AI again, right? So you have the t squared term. If you do it without, then it's just the cross terms. Right, and it can verify quite easily that, you know, because of this inequality, right, it's always better to do with replacement, okay, meaning random shuffling is done. Okay, now so this is a case where you can see quite easily, right? Now let's look at the sum of
What's the factor that counts?
There's going to be a conjecture later. That's exactly, there is going to be a general conjecture to say what ought to be true. Okay, I'm going to show it to you right after I present this. When you do a sum of quadratics, again, you know, why is this relevant? Because ultimately, if you do SGE, you're going to do a objective function, mainly of this form, right? Sum of quadratics. Yes. Again, what you try to write down the expected error is going to be something a little bit more complicated. I'm going to assume that the AI are symmetric matrices. So it's going to look like identity minus, you know, the learning rate times AI. Okay. Well, sorry, this should be a J. This should be a J. Okay. Now, of course, you know, as I told you, right, your learning rate is going to go to 0 no matter what. So ultimately, this must be a positive semi-definite. This matrix must be a positive semi-definite. So again, you're looking at expectation of a product of positive semi-definite matrices. And so this led Ben Reck and Chris Ray to conjecture the following, okay, that whenever you have symmetric positive semi-definite matrices A1 to AN, then for any n less than or equal to n, right, this other is involved, right? This inequality must be true, okay? Basically, what it is, this is with replacement, this is without replacement, the error with replacement, the error without replacement, the coefficient matrices in front of that. And they conjectured this, but the structural one, okay? The matrix 2 norm, okay? Now, if this is true, well, at least for the problems that they have in mind, then without replacement is always better than replacement. Now, it's not so easy to check this inequality, okay? First of all, it involves a whole bunch of matrices that you have to pick. Now, there are three numbers involved, all can go to infinity. There's an M, the number of terms, the number of summons in your SGD data objective function. There's an N, right? Sorry. That's N, sorry. An M, right? And you have a P, right? Each of this dimension is a P by P matrix. If you want to search for counterexample, there are a lot of things to look at. Now, the thing is that no one would think of searching for counterexamples, but I guess people did try, but not because there's a lot of evidence that it is true. Okay. First of all, this algorithm, right? This inequality is called the non-commutative AMGM inequality. Why? Because it's a generalization of what's called the Maclaurin inequality, okay, which is like what you see here, right? The nth root of Sn defined by that sum, okay, of m terms, right? If you look at the first, right, this is always true, right? This statement is always true, right? And this is Maclaurin's inequality. If you compare the first and the last term, then you get exactly the arithmetic and geometric inequality. So this is like the refinement of that. Okay, more generally, if you compare the first and any nth term in the middle, then you get essentially the P equals 1 case for the conjecture inequality of Dan Brack and Chris Ray. Okay, so this is true, right? Because for P equals 1 is true, right? Because it follows from Maclaurin's inequality. Okay, well, for M equals N equals 2, okay, again, it's true. Okay, now this is what Bhatia, right, Rajendra Bhatia, who's a world expert on matrix geometric mean inequalities. Now we asked him this problem before. He said he has no idea whether it's true. Okay, but he did prove the special case M equals N equals 2, right? And he proved it in a form that we think is very clever. Okay, he doesn't just use the original form, okay, which involves spectral norm. He converted it into a form that involves the Lerner order. That's the stochastic Lerner evolution Lerner, right? Same guy, right? And so basically, he wrote it as an inequality directly involved the matrices and not in terms of its eigenvalues. Okay, but it's sort of easy to show that they are equivalent in this case. So the basic idea here is that it helps to convert things to this form, okay, involving the Lerner order. And basically that's what a student of postdoc of Amit Singer did. So what he showed is that what he did was precisely to do this, okay? Take the general inequality and convert it into an inequality involving matrices, okay? And Lerner order, okay? So this is what he showed was true, okay? That if you take symmetric positive definite matrices, and if it satisfies this constraint, this linear constraint, the sum of the, note that this can always be done, but it introduces a constraint. This is a problem, okay? This is why I cannot. Later on, it's the reason why I cannot just apply the standard non-commutative Posh-Lanzas. Okay. The thing is precisely because of I need to deal with this. Okay. Now the thing is it becomes actually a neater form in my opinion. This form is unique. It says that if I sum all M composed of distinct AIs from this list, then it's upper bounded and lower bounded in the Lerner order by this constant factor of identity n factorial divided by n minus n. Okay. Now the thing is, based on this, people establish like other cases, like for instance, the m equals 2 and p arbitrary. Note that the Bhatia case is m and n are both 2. Okay, so it's true, right? And we actually improve this m equals n equals 2 case. So this factor can be improved to 1 quantity. So actually, this is telling us that this thing here, this factor here doesn't need to follow the conjectured version. Okay, it can be different. Okay, and this is how we ended up ultimately disproving this conjecture. We show that this number can be bigger than 1. Okay, now the thing is, you can actually do it for n equals 3 too, but basically all the evidence are in favor that the conjecture is true. And there's extensive numerical simulations, right, that the authors did. Right, it's attracted some amount of attention. As I said, this conjecture is fairly important to decide whether it's better to sample with or without replacement. That's what people are interested. Now they also prove, well, using random matrices that right? Certain type of random matrices, it is going to hold with high probability that conjecture inequality. Okay. Now, even if you knew in advance that it is false, it's kind of hard to just find a counterexample. Why? Because the thing is, all these numbers n and p can be arbitrary, right? Even if you know that you do not know, you can exclude, of course, the small number of cases where it's known to be true, but the remaining numbers of n and p are still infinite. Now, so we'll show that it's false, okay? And it uses algebraic geometry, okay? Low-brow algebraic geometry, okay? And the tool that we need is something that every beginning by student in algebraic geometry would learn. Is the Hilbert-Nussbaum ansatz, okay? Well, put it in a concrete form. Of course, there are highbrow ways to state this. So in concrete form, it says that if a polynomial, complex with complex coefficient, vanishes on a variety, okay, a set cut out by other polynomial equations, okay, then the only way this can happen is if I raise that a vanishing polynomial to some power, it can be written as some kind of a linear combination, but with coefficients coming from polynomials of those generators. Okay. Now, obviously, the converse is obviously true, right? This is and this must be zero, so this is more like a if and only if condition, right? Now, the thing is, what's not so well known, well, which is what I was telling you was surprising to me, right? If you do it for complex, right? What is the next field that you would think of doing? I don't know, to an engineer, it would be reals, right? Reals are obviously more important and complex. But of course, in algebraic geometry, that's not how it works. Right? People start to do like periodic fields and function fields and periodic function fields and all kinds of esoteric fields. Right? People don't really care about reals, right? But it's important, as I said, right? Real numbers are important in engineering. Everything is done over real numbers. Even complex arithmetic is done with real numbers. Okay, now so IEEE floating point standard doesn't have a complex standard. It's all real. Okay. Okay, so however, it's known, okay? There is something called positive ansatz, right? It's a mouthful, always have trouble pronouncing it, and which is sort of an analog to the Nussbaum ansatz, says that if F is strictly positive on a compact semi-algebraic set, okay? Most interesting sets are not variety, okay? Most interesting sets, and that are practical, right, are semi-algebraics. So it's important to talk about the semi-algebraic equivalent of this. So if I have a compact semi-algebraic set, meaning defined by polynomial inequalities, then there is a sort of a statement that's more or less true, right? But with F positive, right? The most standard form is that you can write F, right? You don't have to raise it to power, as a more like a linear combination of these Fi's, okay? The Fi that defines the semi-algebraic sets. But now, I have to take a product of a Fi, right? With a power of 0, 1. Okay, so this sum is going to have 2 to the k sum. So this is exponential left, okay, unlike the original one. And the coefficients, right, the sigma, are what's called sum of squares polynomials. These are polynomials are automatically positive value everywhere. Okay, they are sum of squares of polynomials over the real coefficients. Okay, this is what I call sigma squared. Okay, x1 to xn. Well, there are many variants. Like, for instance, there's one with Kutina that sort of reduces this exponential sum to just a sum that has only k terms, but requires some mild assumptions on the compact algebraic semi-algebraic set. There is conditions where it replaces this strictly greater than 0 by greater or equals to 0, or negative. That's a little bit less elegant than this, but we can do that. Of course, there are other variants of the lenses too. So now, for us, none of these are useful, right? Because why? We do have a polynomial, but it's a polynomial in matrices. Okay, my variables do not commute. Okay, so I need to look at polynomials in non-commutative variables. Okay, or what I would call non-commutative polynomials. Again, some people call this free variables, right? Variables x1 to xn, where xi and xj are not, it's not equal to xj xi, right? So we just call them variables, right? Because free means something different, right? To most people, free means you don't have to pay for it, right? Here, free, it's definitely not free. Here you pay dearly for this non-commutativity, for the fact that they don't commute, okay? Now, because why? Because as soon as the variables don't commute, you have to keep track of every order. Okay, so there's a lot more monomials that you have to keep track of when you write down a non-commutative polynomial. Okay, I'm going to introduce this, but it's not, I guess it's standard notation. When you put angle brackets, that means the variables don't commute. When I put a D here, that means I'm just restricted to the dose of degree less than or equals to D. Now, this is, as I said, we pay dearly for the fact that the variables don't commute, right? The dimension is much bigger than your typical dimension of the ring of commutative polynomials. Now, there's also certain hooks, right, that you have to deal with. Now, the thing is, this notion of a transpose, right? Think of them as matrices, but it's exactly the matrix transpose that flips the order of a product in a monomial. But this doesn't. It's not something you have to worry about for commutative polynomials, right? Because it's they're always the same, right? Now, so the transpose of a polynomial, it needs to be defined. Now, and I can define this operation by extending it linearly to the set of all non-commutative polynomials. And it happens to have this property that F transpose is equal to F, then we call the non-commutative polynomial symmetric. Okay, note that it's not the same thing as a symmetric polynomial in the usual sense, in the sense of a commutative, the usual commutative polynomial. Okay, this is always satisfied, right? So this is just symmetric in this sense, F transpose to F. Why is that important? Because if I evaluate F, right, this non-commutative polynomial F on matrix arguments, right, that are symmetric matrices, then this, the result, the output is a symmetric matrix if F is a symmetric polynomial. Okay, so that's very nice. So if you have a symmetric polynomial, it always takes symmetric matrices to symmetric matrices. Okay. Now, so also going to be interested in a special case when D is equal to 1, the linear polynomials. These are nice because they are always symmetric. And it's important in particular for me because in the rate-ray conjecture, I have this condition. Okay, so this is a linear polynomial. Okay, now so fortunately for us, now I'm slowly running out of time. There is a form of the positive stanzas for non-commutative polynomials that meets my requirements. Okay, first of all, the semi-algebraic set, the analog of that, the non-commutative semi-algebraic sets are all defined by linear polynomials. Okay, by linear polynomials, and that is exactly the form that you have in rate-ray. But I have this condition that this semi-algebraic set must be bounded. Okay, if you know Cucina's positive stanzas, this is natural. This is obvious why you need this. Okay. Now I'm also going to define something called the non-commutative sum of squares generated by a set of linear non-commutative polynomials. It's given by this. Okay, it is, what is this? In some sense, the best way to think about this is to look at the commutative analog. Okay, I have a sum of squares, like all these terms in here are squares of monomials, and I have some coefficients. Okay, so these are these are non-commutative polynomials, so think of them as matrices. Okay, so I cannot write Fij squared, I have to write transpose times Fij transpose Fij. This Li so the coefficients. Okay, now the thing is that I am only interested, this result can be stated more generally. It's by Houghton, Clark, and Rudolph. This non-commutative positive stanzas can be stated more generally, but this is all I need. Okay, I just need it for the special case where BL, right, this set, semi-algebraic set carved by linear polynomials, as long as there's non-empty interior, it's bounded, right? It's bounded in this sense. Then there is a positive stanzas. Okay, a polynomial, symmetric polynomial, is non-negative, right? For every element in this sort of is non-negative on that non-commutative semi-algebraic set, even only if it's a sum of squares. In this sense, okay, it can be written in this form. Okay, it's a fairly deep result. Okay? The original result by Houghton, right, doesn't have constraint. It doesn't have this outing. It's defined on that. That paper appeared in an Annals Journal. Okay, that's a fancy journal, right? As far as I'm saying. Yeah, right. And this is deeper. Okay, it didn't appear in a fancy journal, but it's deeper. Okay, it implies that as a very special case. Okay, now so to avoid clutter, I'm just going to introduce this notation when I sum over do without. I'm going to write sum Ji equals Jk. Now, given this non-commutative quantitative answers, I can now write my rate conjecture as a minimization problem. Okay, remember, I need to figure out whether these coefficients are indeed given by n factorial divided by n minus m factorial. Okay, I'm going to drop the identities for clutter. So that means I want to find the smallest lambda that I can put here. I want to find the largest lambda. No, the largest lambda I can put here, the smallest lambda I can put here. Okay, that leads me to this two statement. Okay, I want to minimize this. Well, so the rate conjecture is equivalent to the statement that these two numbers must be bounded by n factorial divided by n factorial. And we need one other two. Okay, so far everything is theoretical. They prove that some problem can be restated in some other form, right? But there are no numbers involved, right? Ultimately, right, computational math, you need numbers. You need numbers with decimal points. Okay, you need floating point numbers. Otherwise, there's nothing. Okay. Now, so we're going to do a little bit more. I'm slowly running out of time, so I'm just going to say that you can further transform this. Okay. You can transform that optimization that I've written down on the previous slide ultimately to this form. Okay. So basically, this xi here is a placeholder for your what you call the linear constraint. What the functions, the variables you optimize over are this yi, this was the xi, is this placeholder, right? Carry of that lambda. Okay. Now, the good thing about this is that this problem is what's called SDP, is semi-definite programming problem, right? And can even cast it in sort of a very concrete forms, right? As I said, xi can be eliminated, it's placeholder, so you can cast it in what's called standard form. Okay, so you minimize essentially linear functional over the positive definite form, right? The symmetric space of symmetric matrices, were subjected to constraint. Okay. What's known about this kind of problems is that it can be solved in commutative time. Okay, so this is a special case with m equals n equals 5. Okay, two, three numbers. Okay, so p is still arbitrary, but n equals 5. Okay, now what we did was show that this is this minimum, but we have two numbers, right? Lambda 1 and lambda 2. One of the numbers exceeds the bound that was conjectured by the rate. Okay. So if it's correct, if the conjecture was correct, then this would be 120. It's not, right? In fact, we got 120 on top, right? The upper bound is right, the lower bound is wrong, right? Now, so the thing is, it says that when n equals 5, there must be a counterexample, right? Now, so and indeed, it tells you where to look. Okay? It tells you that when n equals 5, you can find counterexamples, and after we disprove this, people have looked, thought. Okay, so basically, this is the idea, right? And got floating point numbers, so I'm done with my go, right? So this is the paper in which that result was disproved, right? It involves algebraic geometry, some amount of algebraic geometry. Ultimately, it reduces to something that requires check by computer, which points to like where you can find counterexample. Much.
It's like there was number 1, for which like it was shot, something was shot.
Yeah.
So
Basically, the original problem looks like this, right? This was what it looked like, right?
Yeah.
Okay. Now the thing is, what I did was to try to put this in a form that can be converted to a problem that is standard in optimization, which involves finding the largest number that I can put here, right? This number, right? And the smallest number that I can put here. So the thing is, the smallest number that I can put here, it's not correct. It's not 120 and it's 5. But the largest number that I put here, it's bigger than negative 120. Oh, it's smaller than negative 120. So that means the conjecture is incorrect.
But does it mean that if you give up on the bottom side of it, you will still have a conjecture?
Yeah, to some extent that's true, right? This part of the conjecture remains unverified. Okay, but I guess knowing that it's not correct, why I guess people lost interest in this. I'm not sure if anyone is still attempting to prove this side of the inequality. We don't have a counter example for this side of the inequality.
The other side looks as if it's correct, it's shot.
Yeah, it does. It does. Right. So maybe it's correct. Okay, maybe it's correct.
And is it less correct?
Well, but the thing is, you should remember that this wasn't the original. The original conjecture is one-sided. Okay, we split it into two sides. Okay? So this is not we, but John split it into two sides. So that's why, and we said that this side is wrong. Okay,
Yeah,
that's
what's
right.
one side being like correct?
Well, so if you have the one-side version, it says that this example is wrong. This inequality is incorrect. Right, because there is no two sides, right? We sort of refine it and show that one part is wrong, right? Essentially, this is on one side. It shows that, yeah, you don't. Yes.
What is line on the something with the placement? I rather, one side, I think that one side is opposed to the other doesn't make this. What is that?
I'm not sure. The thing is, first of all, this version that's stated here, there is no, I should say, like, if you look at the previous example, right, you might have noticed that the norm is inside. Okay. Now the thing is, I have no idea why they put the norm outside. Why they had put the norm inside, and then actually my strategy doesn't work. Okay, but they put the norm outside. This was their paper. Now, but because of our work, right, somebody, the star, right, from Cornell actually went to look for an n equals 5 example, and his example shows that even if I were to put the norm inside the sum, it's also false. Okay, so it's false in multiple ways. I suspect this is too good to be true. There is no, I don't know, not neat inequality. I guess this is definitely false. Okay, no,
This doesn't imply that there's something. It doesn't imply that something. What does it imply something?
yes. So of course, the thing is, first of all, it's in order to state, for people who are not in applied math, conjectures are not that common in applied math. People don't state conjectures in some field. This is one of the very rare instances where I actually see a conjecture. Okay, and one reason is because the conjecture doesn't actually capture everything that's here. Okay, this is only like a very special thing. This is only saying that this is a projector, right? Projector happens to be a positive semi-definite matrix, and therefore they say that it must be true for all positive semi-definite matrix. There's no reason to think that. Maybe it's true for projectors, okay? Right? So there's still a lot of unanswered questions. So I'm not sure that it's really saying that, right? That is what they said in their paper, right? If it's true, then without replacement always beats with replacement. A bit tenuous, okay? I agree. Yes.
Actually, that was my question, which is, I thought the original question that you wanted is, yeah, it's a projector, it's not.
Yes.
So
Exactly.
that's why. I was-
Exactly. Thank you for pointing that out. Okay? Yes.
But
Yes.
yeah. Now that, so if I understood correctly the logic, the projectors arise in a very specific problem.
Yes. There's also that too. There's a one-dimensional projectors, right?
Presumably in other problems, you would get other problems.
Yes, like I said, it's not so common to find conjectures, but we found one, right? And the conjecture, at least their conjecture statement is false. And we are sort of happy to show that they are wrong. Okay, we are not trying to help them correct their conjecture. Okay, that's maybe some of you will be interested to do that. Okay, but I didn't actually look into how else I could modify their conjecture so that it becomes correct. Okay, for instance, the upper bound could be correct, right? Yeah. Yes. Yeah. I've never thought of it, right? Maybe the good thing about this is that it's homogeneous, right? It's inherent understanding, right? It's given by all the same factor, right? It's true, and the sort of is important, right? In order to get this equivalent conclusion, my solve have to be able to scale my matrices so that they satisfy this inequality, right? So, and as I said, right, I don't care whether it's, I'm not really that interested in fixing their conjectures for them. Okay? Yeah. Yes, Matic?
So
Yes.
so you know this, so if when compared here to SVG, we know that accelerated energy is actually up.
it's already, it wouldn't be fair, I didn't give you the full picture, okay? Now, my algorithm actually already includes SVRG. It uses control variant. Right, every couple of steps is actually just that, right? So this is SGD is the only one that doesn't use the SVRG. I mean this variance reduction strategy of using control variant, right? So everything else uses control variant. So I try to push everything to its
How should I interpret the primitive? I mean, so the fixed SVRG is m plus square root of the addition of r times n. So how should I interpret the primitive on the previous slide? I mean, here you have all kinds of higher exponents for condition.
yes.
So accelerated SVRG only has square root condition. It's actually square root condition of the square root n. So that's where, and we know that's up. So I mean, this confuses. You're comparing. Why are you not comparing to?
Well, so I guess the thing is SVRG also doesn't have like correct me if I'm wrong. The learning rate is not specified. Right? You have variety of ways to pay, right? SVRG is simply SGD with control variant. That's it. Okay. Now the thing is if you want to specify, a learning rate that sort of depends on a function, right? Then essentially there are three possibilities. That's at least the ones I know of, this plus F of Y, limited LMDFGS, right? And mark hours, right? So we compare essentially with this. Right. So I guess in this picture, SVRG is probably done with fixed learning rate 1 over n, right? Eta k was 1 over k, and SGD too. Right? I have to ask my students, but obviously they did this. Yeah. So the thing is, there must be some assumption because what do you mean by Eta k, right? What do you mean by learning rate? What is your learning rate in SVRG? It's unspecified. Okay, it just says that you must have this certain, maybe you have some convergence condition. Say, yes. Yes. Yeah. Okay.
I mean, I can believe that empirically better,
So,
but this is an exact learning rate that will give you square. I mean, SVRG is condition of error. With summation of square condition of error. There is an exact learning rate.
So I would be happy to get that reference. Okay. Right. So you must make an assumption on Eta k. Otherwise, I don't think it's possible. There must be further assumption than just this. Okay.
Specific. Okay.
In SVRG? Oh, okay. Well, couldn't be in Tong's paper, right? Because Tong's paper doesn't have a specific Eta k, right? Okay. So, well, it depends on what you mean by SVRG. I'm talking about the original person who created that algorithm. Okay, and okay. Very much for your attention.